Thank you. My work that I was previously doing at Harvard and now I've moved to Caltech focuses on quantum error correction with arrays of trapped atoms. And I will focus today on one particular paper we recently wrote because it's very long and I want at least some people in the world to know what's in the paper. That's what the main focus will be, and it'll be kind of an intense talk in some ways, so I hope, sorry for all the technical details. Another aspect is that there are so many interesting aspects of quantum computation and of quantum error correction, and what's perfectly in the theme of this conference is I think it is one of the most remarkable aspects of modern physics, at least in my personal but slightly biased view. And this talk will also be much from the lens of physics for understanding how quantum error correction works. And broadly, starting at a high level, quantum information is fundamentally much harder to store and operate on. If you have a classical bit, you take pictures of it, it gets redundantly copied in its environment. If you have a quantum bit and you take pictures of it, it collapses. And similarly, if you take a chain of spins and you use them to, for example, very finely tune their interactions J, you can get out some quantum computation. And you can get out some answer to a question you're interested in. But if J goes to J plus epsilon, you can go to a completely different state, and you become very sensitive to small imperfections. And this is not unique to quantum systems necessarily. It's also true in analog classical computers, which in principle can actually be very powerful because they represent continuous real numbers. But we don't use those. We use digital classical computers, at least for the most part, that are composed of these digital robust building blocks, or these bits, that can be, that are naturally protected. If you have some voltage and it's 3.3 volts or 3.4 volts, it all gets corrected to bit 1. And this seems at odds with what we have in quantum mechanics, where one of the things that makes our computers powerful is that we get these continuous or analog rotations on our block sphere, but these are very sensitive to imperfections. And there's a lot of fascinating history going on here. Starting, I would argue, all the way back in 1961 with this famous paper from Landauer talking about the role of dissipation in standardizing signals and making computers work. And this seems really at odds. So here, one of the things we understand is dissipation is really important, because it erases history. It allows you to do things in a robust way. And so you need dissipation in order to stabilize. But quantum mechanics is unitary. You can't dissipate without destroying information. And that seems like a real challenge, because now we see that quantum computers are powerful due to the exact same underlying reasons that they're really sensitive to errors. And that sounds like a paradox that is hard to solve. Remarkably, you can solve it by using quantum error correction, and I think it's quite remarkable that it's physically possible at all. And the way that it works is you use entanglement to store information non-locally, where you take a single logical qubit degree of freedom and you delocalize it over many individual physical qubits. And by being so delocalized, this information now becomes protected from the environment. By measuring products of qubits, or so-called stabilizer checks, we can detect errors while preserving the encoded information. And the thing that I think is so remarkable is the way that we solve this paradox is you can do coherent unitary evolution on the logical information stored in the entanglement while applying dissipation to the underlying physical qubits. And that's just amazing. And we're going to go into, all the different things that you have to do in order to be able to do that, to do arbitrary but protected universal computation. And the fact that this is so amazing, I think, is well captured by a famous argument in the early days between Shor and Landauer, where Landauer was very publicly criticizing Shor for a lot of these new ideas, saying that this is just analog computation, we know we can't correct analog computers, what's new here? And Shor's response is that the computation is analog, but the errors are digital. And it really goes back to, the wave-particle duality is really one of the core reasons of why quantum computers are so powerful. We can do wave-like computations and analog-type computations, but we can correct the system as if it's a digital system. And I think it's really a very exciting, scientific and physics frontier. It also has really exciting technological applications, but it's really, I think, quite remarkable physics that we get to see for the first time. In our explorations of quantum error correction and quantum computation, we use neutral atoms trapped inside of optical tweezers. And in particular, we use this approach we like to call these reconfigurable atom arrays, where we have these atoms trapped in optical tweezers. Their information can be stored for very long times inside of this robust hyperfine qubit inside of the atom. And we can entangle two atoms by zapping them with this global laser pulse that excites them to this so-called Rydberg state, this very high-lying orbital state. This causes them to entangle. And then the coherence is so long that we can actually move the atoms around in the middle of the computation. This is the first quantum circuit, or one of the first quantum circuits we did with this approach back in 2022. And we made here a Tor code on a torus, so with long-range connectivity. And the way we have this here is we have 16 data qubits fixed here. We have 8 ancilla atoms moving around the system. Here they're doing a stabilizer check, and they move all the way across the system here and make periodic boundaries. This is a real movie of the atoms taking camera pictures. It's really fun. And especially if you have amazing colleagues like Harry, who's starting a lab at Berkeley, for anyone who's interested. So the two really unique opportunities from this approach is that you have non-local connectivity, which, as has been prominently featured in this workshop, is extremely useful for quantum error correction. And finally, you get parallel and efficient classical control, where although you have to control many, many qubits, many redundant qubits to make one error-corrected qubit, because they're all supposed to do the same thing anyway, it's something that you can do in a parallel and efficient fashion. So using these approaches, back in 2023, we studied error-corrected algorithms in the lab using this, first-generation zoned processor we have. And the way this works is we have logical qubit blocks stored in storage zones, and then when we want to entangle them, we pick them up from the storage zone, move them into an entangling zone where we can entangle them on demand. Then we can move logical blocks from this entangling zone into a readout zone, et cetera. And really the big focus was on doing parallel control over logical blocks and really starting to think about the processor as being controlling not over individual physical qubits, but over individual logical qubits. And in terms of some of our experimental findings, I think that was really the central one that cannot possibly be emphasized enough. We did all these experiments with just, a few PhD students in the lab, and the reason that we're able to do this is because this is the first logical circuit we ever did where we made a GHG state out of logical qubits. We're not thinking about doing a complex physical circuit in the lab where we have to think about what are all the individual atoms doing. We just think we have these big blocks and we can operate on them with these big logical degrees of freedom just in these big coordinated motions. And here's how we made a logical GHG state where each line here is a logical qubit. That was one of the really important findings we had. Another was the importance of considering the algorithm as a whole, which allowed us to make a variety of theoretical advances in terms of how we can improve overheads and error correction and save so-called D rounds in the number of error correction rounds we have to do. We learned about the importance of fault-tolerant compiling, where we can tailor error correction and algorithms to each other. The fact that errors are digitized when you do error-corrected algorithms. And broadly, I think something that we're really experiencing is a transition in the theory that we do from focusing the algorithms that we study to error-corrected implementations, and focusing the error correction we study to the implementation of algorithms. And that's been something we've learned a lot from. Take a quick pause for questions. Okay. So that was at the end of 2023, and there's been a lot of exciting progress since then across many different systems, from trapped ions, superconducting qubits, neutral atoms, and I think it's really, I think it became extremely clear in 2024 and in 2025 that error correction clearly works. That is something that I think is no longer that interesting of a question. I think it clearly works at this point. And then now the question is how to do the whole thing. So, so that was our first goal, was to start doing error-corrected algorithms in the lab and see what we learn. And our second goal is we really want to understand what are all of the individual things we need to do to build a universal fault-tolerant quantum computer. And to recap one more time on a physics level, what we have to do conceptually is we need to dissipate errors on the physical qubits while doing arbitrary unitary evolution on the logical qubits stored in their entanglement. That's amazing. And there are many mechanisms involved. And here, in order to be able to study what are all of the different things we need to do for building a universal fault-tolerant computer, we did what we believe is all of the things you have to do, studied how they all work. So that's what we're doing here. We'll implement for the first time all elements we need for a universal fault-tolerant computer. And by studying the underlying mechanisms of how these all work, we find significant simplifications to the error correction and architecture, and we also see some really cool physics. So I believe David is here. Hello. Hello. Yeah, okay, sorry, being awkward. Okay, here are the 4 things that we think you really need to be able to do, and I think they're actually beautifully summarized in this paper. I actually always have this reference here, it's not just for you. Sorry. I always see, like, how far can I go in my talk before I start being really awkward? Okay, sorry. Here are the 4 things that you really need to be able to do. So when you do computation, it's imperfect. And so you need to be able to remove entropy, as was discussed yesterday. And you also need to be able to do this below threshold. And what that means is that you can start to exponentially suppress errors as you increase the size of your code. And that's a really important way to be able to get logarithmic overheads for realizing arbitrary computations. We also need to be able to do fault-tolerant logic, which means that as we do logic, physical errors don't spread and become logical errors. We need to be able to, although we have the digital building blocks, be able to realize arbitrary unitary operations with our logical degrees of freedom, not just the specific ones that are given to us by our code. And finally, we need to be able to do deep circuit quantum computations while ensuring all physical errors are removed. And yesterday, this was highlighted as the importance of being able to do reset. So this paper is very long. So here's an overview of all of the things that we did. So one is we studied the mechanisms of entropy removal, where we studied how if we subject an error correcting code to noise, and we do here on the distance 5 surface code, we do repeated rounds of error correction, we see that the error correction removes errors both due to a Zeno effect, as well as by removing entropy from the system. Yes, please.
Can you say a bit about what code you're using?
Great, yeah, so, okay, phenomenal. So here I will show now many codes. This is a distance 5 surface code. Yeah, thank you for the question. We studied here a variety of different error correcting codes to explore various different aspects. Yeah, thank you so much for the question. So here with this distance 5 surface code, we studied the different physical mechanisms that underlie entropy removal via stabilizer measurement, which is really, that's the core purpose of doing repeated error correction, is to remove entropy from the system. And it's really important to be able to do that below threshold. If you can do that below threshold, it allows you to suppress errors, and this was beautifully done by the Google team roughly a year ago, and also here we're at roughly a factor of 2 times below this error correction threshold on the surface code, such that as we increase the size of the code, the performance improves. Here, just from distance 3 to distance 5, we have an error budget and pretty good understanding of where all this is coming from. So this is how entropy removal works, just with the, a code idling. What's really important is that to understand how entropy removal happens interspersed with doing fault-tolerant logic, and because, logic is imperfect and removing entropy from that is really the main purpose here. And we study this in many ways that I will describe in a few slides, as well as not just doing fault-tolerant logic with entropy removal, but ensuring that we can actually synthesize arbitrary unitary operations on our logical degrees of freedom. And finally, we set up an architecture in a way that allowed us to do deep circuit computations while ensuring that all of our physical errors stayed constant and our entropy stayed constant. And here, doing quite simple, but deep logical algorithms with up to roughly 1,000 logical teleportations. And all of these things combined, what it really has allowed us to do is have a quite a bit simplified framework and architecture for achieving an understanding, for achieving all the ingredients we need for scalable realization of arbitrary algorithms. And when I say scalable, I mean polylogarithmic overhead, where you need, for example, the arbitrary unitary synthesis, you need the exponential error suppression, and so on. So we studied many different error correction techniques that are all described in this paper. So ranging from generalized techniques for syndrome extraction, using erasure information and machine learning in decoding, lattice surgery and transversal operations, efficient transversal unitary synthesis and code switching, as well as high rate encodings in deep circuits with dozens of logical qubits and hundreds of teleportations. And what we got from all this are understanding the underlying mechanisms and all the core elements for universal fault-tolerant computing. And we have significant improvements and simplifications to our architecture design that I think make things quite a bit simpler. Let me take a quick pause. Yes?
So the bottom left here, what does it mean for the signal around the error store?
So this one I will describe in like 2 slides. Great question though. Yes? Yes, so here we studied entropy removal in multiple contexts, and this I will also go into in 1 slide. But in all of these different situations, entropy removal is really one of the core things we were focusing on. So here we were just doing repeated stabilizer measurement using Ancillus on a distance 5 surface code Here we were doing repeated stabilizer measurements on a distance 5 surface codes interspersed with fault-tolerant logic. Here we structured the circuit in a way that the entropy got natively removed every time we did logical teleportations, which for doing deep circuits with many teleportations but ensuring all of the errors get removed from the system is something that ended up being quite native. And here what we did was structure the entropy removal in a way that is exactly suited to when we do universal operations, we have to do teleportations and the entropy can natively get removed as long as we set it up correctly. So we did it in many different ways, but the kind of theme is always making sure that errors can't continue to propagate throughout the system. And entropy just has one way to get, go into some type of sync. Okay. Yes. Physics style talk of error correction. Okay, great. Thank you so much for the questions. So, okay, in the simplest format, let's, just explore how does, we've theorized error correction 30 years ago. Now we're so lucky that we get to study it in the lab for the first time. I think the physics is remarkable. Before, we start, it should be a very technologically useful tool, but I think the physics is also so amazing. So we should take a second, smell the roses a little bit. So here, what we do to study that is we have this distance 5 surface code encoded in data qubits, and then we have ancilla qubits that we move around in the system in order to do repeated stabilizer measurement. And here what we do is we inject global coherent errors at each unit time step, and we do repeated stabilizer measurements. And what we see is that as we increase the number of error correction rounds that we do, it suppresses the buildup of logical error. And this is due to two physical mechanisms. So one is the Zeno effect. This is something that's uniquely important in quantum mechanics and the role of projective measurement. And the other is that we track errors as they get generated via tracking the state of the stabilizers, and we can isolate these two effects. If we just ignore the ancillas, then we isolate only to the Zeno effect, and we see that that suppresses errors just because we have global coherent errors, but then when you do stabilizer measurement, they project independently into local uncorrelated errors, as well as when we track the ancillas, that's an extra type of entropy removal because you have information about the errors that are present in the system. And both of these are important for the role of repeated stabilizer measurement in removing entropy from your system. Yes?
Was the initial state on the same basis as the measurement?
Yes.
But then how come the zero frequency had the highest error rate?
Because here we're like really injecting errors at each unit time step. So we have some let's call it 20 milliseconds, and we inject errors at uniformly. And then as we do more and more rounds, we do more and more rounds of error correction interspersed in that same time window, and that error correction removes errors from the system.
Oh, so the amount of error in space-time is fixed, and then you increase the number of errors.
That's right. That's right. Yeah, to see how that entropy gets removed. And also here it's greatly amplified by the fact that if you have coherent errors, global coherent errors, they can really build up, but if you do error correction, they get quickly projected. And the fact that it's global is totally fine for the system. Great, yes?
The bottom right, are you still doing this syndrome extraction, just not the gradient cells?
So here we're always doing the syndrome extraction. In the light blue, we just ignore their value. Yeah, great, yeah. In the dark blue, we also just do the full decoding. Great. Okay, as usual, I'm not on track to finish my talk in time. That's okay. Okay, that's what happens with a single qubit. We want to understand what's the role of entropy removal when we do logic operations. And here, in order to study the role of stabilizer measurements, we studied two different configurations of doing logic. One is transversal gates. Another is a more planar or so-called lattice surgery configuration. And here the stabilizer measurements play two very different roles. So in order to probe the role of the stabilizer measurement in the logic, here in the transversal setting, what we do is we pick up these two blocks, put them on top of each other, do repeated transversal gates, do some error correction, repeated gates, etc. In the lattice surgery case, in order to do logic operations between these two blocks, you can't put them right on top of each other, which would otherwise be a very convenient way of entangling these degrees of freedom. So we have extra ancillas in the middle, and we measure the product of these three ancillas in the middle, and if we measure them correctly, we get out this Z1, Z2 string on these two logical blocks, and that's how lattice surgery works. So you use ancilla measurements as a way to entangle two logical degrees of freedom. And for this reason, The lattice surgery situation is significantly more sensitive to ancilla measurement error. Here we intentionally inject ancilla measurement error just in post-processing by just flipping bits in our mind. The transversal case gets only very slightly worse if we do the decoding correctly. There's a very slight growth here, because it's just corrupting how well we do the entropy removal. The logic is done by the transversal gate, just directly doing the logic between the data qubits. And the stabilizer measurements are responsible only for removing entropy. And since here it's not that deep of a circuit, if the entropy removal gets slightly worse, it only slightly degrades the performance. Compared to the lattice surgery case, where if you don't measure the stabilizers correctly, you just won't do the right logic operation. So the stabilizer measurements play very different roles in this transversal and lattice surgery case. And understanding these different physical roles is really important for understanding different aspects of your error correction architecture. Where, for example, in this transversal case, the logic gates are realized directly between the data qubits. In the planar case, the logic gates are realized via ancilla stabilizer measurements. So here, stabilizer measurements are solely there to just remove entropy from the data qubits. Here, stabilizer measurements are extremely important to get right. And so you really have to make sure you repeat them d times. And here, measurement errors are benign, because all they're being used for doing is removing entropy. If you just track how errors propagate correctly and do the decoding properly, then it's something that you can be robust to, because the physical role is just removing errors. So in this transversal setting, stabilizer measurement only removes entropy. This gets rid of this d rounds of error correction required in a conventional case. You should also ask Alex Kubica, who is also an expert on this. He's in the audience. And that's one thing that's apparent from this comparison. Another thing is that, the way that we even think about basic things like logical gate fidelity, really need to incorporate concepts like what is the physical entropy inside of the system. So here, for example, what we do, so to answer your question from earlier, is we vary this number of n C0s that we do in each round. And if we do many, many C0s per round, then we overwhelm the system with too many errors. If we don't do many C0s per round, then now we're injecting a lot of errors from our error correction procedure, but we're not doing as many logic gates as we could. And there's an optimum here experimentally around 3 C0s per error correction round, where the errors we inject from doing the logic gate roughly balance the errors that we remove from doing the stabilizer measurement. Okay, let me take a pause. AF, fantastic, is the acceptance fraction. Here we're doing some sliding scale post-selection, where the light blue is we keep all the data, and this darkest one is we keep 13% of the data. So it's like some sliding scale error detection that slightly improves the local error density in the system. Which is just a way to forecast what will things look like when we improve the physical fidelities by a factor of a few.
Just to make sure. On the left side, you would still need to repeat the measurements eventually if you have the code, like if you have measurement errors in your system. Asymptotically, you might still need order of d rounds of measurement. It's just that you did the gate. You don't have to wait to do the next gate, perhaps, like you can keep doing the gates, but after, let's say, you're done with all the gates, then eventually you would still need order of d rounds. While on the right side, you're saying you need the d rounds immediately. Right?
So I don't quite agree, and it depends on the context. So here, for example, in this circuit, you don't need the d rounds at all. So it depends on what exactly you're doing. If you're doing like a Clifford circuit of depth 10,000, you're going to do roughly 10,000 transversal gates. You're going to inject a lot of error, and you need to remove the error. But imagine that the code is size 100 or size 1,000,000. Why should it matter if it's size 100 or size 1,000,000? You're generating a little bit of entropy here. You need to just remove the entropy as it goes. The role of stabilizer, here, the stabilizer measurement, for example, like grows an operator or connects to operators. That's the role. Here, the role is just remove entropy. It shouldn't depend on the size of the system, as long as you're doing it properly. There's other contexts also in a second, for example, to create something like magic. There, the stabilizers do yet again a different thing, and then it might change. But yeah, does that answer the question? It's really helpful to understand like what are the physical roles. And actually, I was very inspired by this 1999 paper. I think it was very helpful for understanding a lot of these things. Okay. Great. Okay. Also, but things like logical gate fidelity, if you ask what the logical gate fidelity is, it's It's a variable number. It depends on how you think about things, because it's not, this logical qubit, or the physical qubit, fidelity is either do the right thing or you do the wrong thing. And it's a very stable concept. Here, you have this logical degree of freedom, but you have all these internal degrees of freedom represented by the entropy in the system. So something like gate fidelity has to be, entropy dependent, and you have to also capture the rise in entropy that when you do each logic gate. This is something we modeled in the supplement of our paper. So that's useful for understanding how does entropy removal work in the context of a single qubit, as well as when we do fault-tolerant logic. But we'd really like to understand how to do fault tolerance for arbitrary algorithms. And here, what's really important is we need to be able to do magic. And magic, we find, as has been discussed extensively, but here we're find experimentally, is extremely unique and plays a very interesting role from a physics perspective and how it connects with all of these concepts. So to study this, here we made 3 different configurations. So one is a 3D color code, or a 1513 Reed-Muller code. It's this famous code that has a so-called transversal T-gate. This T-gate is just a 45-degree rotation. That's this magic that we like to say. It's not a made-up word. Then we have 2D color codes, so 713 codes, as well as physical qubits that we analyze as if they were 3D color codes. And then we make these different systems, and then we subject them to some global phase rotation, and then see how they respond. And in the context of the physical qubits and the 2D color codes, the X logical expectation takes on plateaus at 0 and 0.5, or like 0 and pi half and pi, etc. If we make 3D color codes, then actually we get an extra plateau at these fractional values corresponding to their transversal T-gate and corresponding to a pi quarter rotation. But importantly, for example, if the 3D codes have the wrong stabilizer signs, then this extra plateau goes away and you lose your robust transversal T-gate. And one of the things that, and I can answer more questions about this toward the end because I'll have some other kind of crazy comments, but the stabilizer measurements in the transversal case are used for removing entropy. That's their role. Here, the stabilizer measurements really need to make the right structure of entanglement. And there's actually a really deep link between the logical magic that you can make as well as the physical entanglement that is present in the system, which I think is quite remarkable. And I'll say more about that at the end. Yeah.
I just want to make sure, so you initialize your, in your 3D color code, say, or your 2D color code, you initialize in the code space, you're then doing just a global rotation of all the qubits, and then measuring the stabilizers again, and then this graph is computed from, so the red line is computed from those results in the 3D color code where all of those stabilizer measurements have the correct value?
Where we intentionally prepared the stabilizers as having all +1 expectation values, and in the gray is when we prepared them as having -1 values. So what they had at the end, we still do error correction.
Okay.
Yeah, great question. Yeah, although that's also interesting. Yeah.
What does that mean for the physical qubits?
So physical qubits, we just subject them to a global rotation.
Some of signals again.
Yeah. And then we analyze them as if they're Reed-Muller codes. But here, in this transversal setting, it's not exactly what we did here, but in a Clifford context, there's actually no experiment you can really do to tell the difference. Because you do, for example, if you do like a pi half rotation, like a Hadamard, then the physical qubits all very conveniently go to the right basis where the stabilizers are finite, and then it feels like this paradox. One of the things we've discovered is this paradox always applies for universal algorithms, for algorithms with the Clifford setting. And the thing that's really unique is that the magic state, that's the thing that really requires the entanglement.
So the logic of the 3D color code, you basically make a 3D color code, but you just initialize the class.
Yeah, no entanglement. Yeah, no entanglement. And for all the Clifford rotations, looks the same. But for up to some subtleties with the escape, but that's not worth going into. So, okay. So that is allowing us to make these transversal T angles. We use these 3D color codes, and there's this interesting role of entanglement. I'll touch on again at the end. But also we can now use this to, for example, synthesize arbitrary unitaries with our digital building blocks. In particular, there's this kind of Solovey-Kitaev style approach where you do this like HT gates, and that allows you to go to many different spots on the block sphere, as has been long expected. And the way that we do this here is with a fully transversal circuit where we take these Reed-Muller codes, we prepare them all in plus logical, we do transversal T-gates, and then we teleport Hadamards with these 3D color codes by doing measurements in the X basis and then a feed forward X. Here the feed forward is just in software, not that it matters for this protocol here. And it's a fully transversal circuit that allows you to have universal operations, which is also seems like a little bit like a paradox. But the thing that I really like about this circuit, from getting to the physical core of how you can do universal processing, is that with measurement and teleportation, it's unitary on the logical level due to decoding and feed forward. The logical information continues to propagate throughout the system, but it's non-unitary on the physical level. Physical qubits go and get measured, and errors can't continue to keep spreading. And this is how this is why it doesn't, quote unquote, violate East and nil. East and nil is only that you can't do a universal transversal gate set in a unitary way. This is not unitary. You do measurement and feed forward. I think it's the most compact way you can write down doing universal processing. Okay, so here we use this to make different angles. This is a polar angle plot on our logical qubit where we do 0, 1, 2, 3 T-gates, and we see, so these are all the different angles we make on our logical qubit that we measure, and we see that as expected. We get an exponential. It's not quite exponential. I should have included the inset. We get a polylogarithmic, to get to some angle correction in terms of how many gates you have to do. But the thing, again, I really like about the circuit, so coming back to these famous arguments between Landauer and Shor, is that, so Landauer had all these early papers criticizing Shor and talking about why it's obvious that you can't do quantum computation, like error-corrected computation. And he has this figure, which is talking about, how a transistor works, where you have multiple inputs that get broadcasted to the same output. And he says, the restandardization used in figure 1 is not available in a Hamiltonian system. Therefore, errors will pile up and the computation will go off track. Excuse me. Restandardization requires erasure of the piled up error. Erasure requires energy dissipation and cannot be performed in a Hamiltonian system. So that's this kind of paradox as to how would you be able to do it. But the solution to the paradox is that it's unitary on the logical qubit level, which is stored in the entanglement. It's non-unitary on the physical level, which I personally find amazing. Yeah, okay. I'm running out of time, so I'm going to keep going. So, okay, with transversal, okay, so this is amazing from a physics perspective, and we can see that you can synthesize these arbitrary unitaries. We also see from a practical perspective that with transversal gates, really the way for us to think about things is that transversal teleportation is like really a key algorithmic primitive. It's the thing that's the underlying, resource behind being able to do universal processing. It's also, a very native source of entropy removal. And for this reason, we set up an architecture to do deep computations that's just focusing on doing as many logical teleportations as possible. And here we did very simple circuits with it. So we have our storage zone, entangling zone, readout zone, and a reservoir. And we take here steam codes. We also made other codes like 1664 codes. We entangle them in a space layer. Then we teleport them with a subsequent time layer. And we keep alternating the system, but in a way where we ensure the errors get removed. And here we do, with these various steam codes, up to several hundred logical teleportations. And again, characterizing this ability to do unitary processing on the logical level, but removing errors on the physical level, we make, for this first plot, a very simple circuit where we just make a 1D cluster state in the time direction. So we make an entangled state just going in the time direction when we do this teleportation-based architecture. On the logical level, we get unitary evolution, and we get correlations between the logical qubits, and the algorithm leads to correlations just as expected for a 1D cluster state. But we get dissipation on the physical level via measurement, where stabilizer errors get quickly absorbed and correlations rapidly decay. We also do this here. So this is for a 1D cluster state. In the time direction here, we have a 2D cluster state in both the space and time direction. And again, it's this physics where, if we want to really make sure that all types of entropy get removed from the system, teleportation is such an amazing building block for doing that. Because if you have like an old block and you do a gate with a new block and then you do this measurement and feed forward, the physical errors stay behind. Like, for example, atom heating, atom loss, all different types of errors you have. And at the worst case, a bit flip error can propagate up to one layer. But the logical information continues to propagate throughout the system. So unitary on logical level, but you ensure that you get entropy removal on the physical level. And it's also the kind of core mechanism behind how universality works via teleportation. And here is a movie of how we do this. So we pick up these atoms, we start to entangle them in the entangling zone. We have a previous group here that has already been entangled. And we take this group, entangle them with the new group, then we put them in a zone. We developed a new technique here. It splits the atoms. This allows us to do non-destructive readout. We have an optical lattice that splits the atoms in half, it's like Stern-Gerlach approach. And they get imaged, and then we see whether what the state was, so that's why they're flickering. Now we'll put the atoms back. It's so satisfying to watch. And here's a movie of, you know, what these poor atoms are going through in order to make this 2D cluster state plot. So this is what's happening in the lab to this atoms. This is not what we were using atoms for in the atomic physics labs 10 years ago. They're really being, yeah, so that's the, each one of these movies is one line. And here we did this with steam codes, but also we did this with up to, you know, with 16.6.4 codes encoding up to 96 qubits. Okay, so to summarize, so we studied here all of the aspects that we believe are required for doing universal fault-tolerant processing, and at least convinced ourselves how to think about doing the whole architecture in terms of universality, removing entropy, fault-tolerant logic, entropy below threshold, fault-tolerant logic, and synthesizing arbitrary unitaries. And we find multiple things in terms of key lessons for us as we continue to think about future large-scale computation. So one is there's a very interesting interplay between entropy removal and logic operations. They have this interesting interplay. It allows us to understand things like logical gate fidelity. It also teaches us lessons such as you should only syndrome extract when you really need to. Don't syndrome extract if you don't have to. Logical operations are imperfect. They create some errors, and then you should remove those errors. That's at least the way it works in a transversal setting. Similarly, you should use entanglement judiciously. Transversal gates and high-rate codes, which I glossed over, allow us to reduce the total amount of physical entanglement, which is a key resource, for realizing a target amount of logical entanglement. And this has a deep link to magic or quantum contextuality, which I'll say in the next slide. And finally, from an architectural perspective, we see that teleportation clearly plays a very powerful role. It's universal with doing transversal, even with fully transversal operations, excuse me. And it also allows you to do things in a constant entropy fashion without additional overhead, as long as you just structure, and constant entropy also, in terms of like atom loss, atom heating, without additional overhead, as long as you structure the circuit correctly, leveraging these teleportations. Okay, and because it's a physics audience, or partially a physics audience, I will say, what's one more slide about this contextuality thing, which I find so fascinating. So we talked about this kind of paradox where, or seeming paradox where it seems that the stabilizers are not that important for doing these Clifford circuits. You have to, the stabilizers are important for removing entropy, but the entanglement doesn't seem to be important for doing these, you know, Clifford circuits or for preparing these Pauli states. But here we found for this magic states, you do need the entanglement. It's like really critically important to have the right stabilizer signs in order to be able to realize this logic, and that corresponds to this magic, and that corresponds to needing the entanglement. And it leads to very funny conclusions. So for example, let's say we wanted to do an error-corrected Bell test where we had like Alice and Bob in two, you know, separate rooms, and they wanted to check that they have a Bell pair. They might even want to use this Bell pair for teleporting a qubit, for example. Then in an error-corrected setting, in order to check their entanglement witnesses, all they have to do is measure their XX and ZZ expectation values to see that they have a Bell pair, an error-corrected Bell pair. And by using this correlated decoding technique that I glossed over, this means that they actually don't even need much physical entanglement within the block in order to see that their Bell pair is actually, you know, shows that it's like XX and ZZ are both, you know, always equal to +1. They get error correction. They're happy. They can even use it for teleporting things, and it shows that they have this Bell pair they care about and the error correction is working. But what if Alice and Bob actually want to prove quantum mechanics is real? Now they want to do an error-corrected Bell test. And then there's this really funny aspect that we always learn about with this Bell test and how it solves this EPR paradox. There's this like funny thing that you have to measure it in the T basis. And then now, if Alice and Bob want to just check that they have a Bell pair, it turns out they don't need much entanglement for the error correction. But if they want to show that quantum mechanics is real and they want to, you know, saturate bounds on how good you can violate CHSH inequalities, then now they do need the entanglement. And this starts to seem a little suspicious. And in fact, in 2014, there's this really cool paper by Howard et al. That showed that the computational hardness of algorithms is linked to contextuality, and this is like still an active research question. Quantum contextuality is about how quantum measurements are correlated. It's similar to this, it's like kind of more of a generalization of this Bell measurement. But here what we find is the minimum entanglement that you need for the error correction is also related to this. It's related to the contextuality, or, you know, for example, doing a Bell inequality test, as well as the computational hardness of what you're trying to simulate. It starts to seem a little bit like a conspiracy, that it's all really just about contextuality. And here we did an error-corrected Bell inequality test that saturates the quantum bound. In a parallel apparatus by Chu et al. And this very, very hardworking atom array 2 team in the Harvard lab, we also studied doing continuous coherent operation on several thousand atomic qubits. I'm obviously running out of time, but here what we were able to do is hold on to atoms in 3,000 atom arrays hold on to qubits in 3,000 qubit arrays for scale of hours, and this is again something I want to highlight. This team worked extremely hard on, but you can see kind of how all these things can get pieced together in the coming years using also these new types of understandings of how to do efficient processing. Okay, so to wrap up my talk, I think it's a pretty exciting frontier for neutral atoms and for quantum error correction. There's a lot of really exciting developments across the field, and it's really incredible error correction progress across the field, both with atoms, but as well as with superconducting qubits, trapped ions, and it's really amazing how all these systems, just right now, you know, start to cross characteristic thresholds, and it starts to become really clear that error correction works. It's a real inflection point and quite a remarkable exchange of ideas. And I think it should be a pretty exciting next few years. So that is the end of my talk. I'd like to highlight 2 things. So three things. Okay, first, the atom array 2 team that worked very hard on this continuous operation. The second thing is I really want to highlight Sasha, who worked very, very hard on these experiments. She's I think now technically in her 3rd year. She was in her 2nd year, and did like really tremendous work on all of these things. And you should really watch out for her because she is quite bright. And finally, I am starting a lab at Caltech, and we would love to collaborate, so please come visit us. Thank you.
For the t-states, question for the t-states. So when you analyze like 0t, 1t, 2t, 3t, what angles do you get? If you insist that you end up close to the z-axis again, right? So 1t is just on the z-axis. If you insist that you end up on the z-axis again, what angles do you get for like small t gates?
So if you insist you end up on the z-axis,
or close to it, maybe.
Well, that's an interesting question. So okay, if you insist it's exactly, then it's just the 45.
Okay.
To be within some precision, I don't know. It starts to chaotically fill, and then we would have to go and analyze it. And it's probably something logarithmic. So go ahead, please.
The answer to that question is well known.
Great. Feel free to chime in. Yeah. Would you like to say, Michael?
I mean, it's logarithmic. Let's not get into it.
Okay. Great.
Any other questions? Okay, if not, let's thank the speaker again.